What we are going to do today is to take a small detour on a topic called probability inequality. This is a topic that you can spend another semester on, just the probability inequality. Now, what I want to do is to talk about a few very basic inequalities that will be used when we study the generalization era in machine learning algorithms. So if you have taken an undergraduate probability course, you may have seen some of these materials before. If not, don't worry, we are going to walk through them together. It will be fairly straightforward to understand these probability inequalities. Okay, so what are we going to do today? We want to talk about two sets of inequalities. One is the basic inequalities using the Markov and Chebyshev results. And then the other one is to use the channel bound and also the Hofstadter bound. Now, these two are a little bit more advanced, which we want to spend more time on. These two are really basic results that we might want to use them often. Okay, so the starting point of the probability inequality is the very simple question. You have a lot of data points, x1 through xn. Think about your error. Okay, so you have a training error, and then that will be measuring between whether your prediction is the same as your true label. So you're measuring yes or no, 1, 0, right? So each one will be a random variable, 1 or 0. And then you have a lot of these. And now you're going to study the average, because we want to look at the average training loss. So that means you need to sum over all the possible training samples and then take 1 over n. And this xn here denotes a random variable. In our case, it will be the loss for certain input data. And then we also assume that all these data, they are independently and identically distributed, or IID in short, meaning that they share the same population mean, where expectation x1 through expectation xn, they're all the same mu. Okay, so this is the error that we want to study, okay, or this is the mean that we want to study. It's called the empirical average. It is just the average that you calculate from the data set. Okay, very simple question that you encounter every day when you do a statistical experiment. You go out, you collect some data, and you say, what is the average of this data set? So what you do is that you go to Excel spreadsheet, and then you crop that column and click a button, and then it sums every number and then divide by the total number of samples. So that is the empirical average. Now, we always know that this empirical average is not the same as the population average, because this is a finite sum. This is the population mean that is calculated when n goes to infinity. So these two are not the same. Okay? And so now the question that we want to ask is, how close is this nu? Okay, so this is the empirical average compared to the population average, mu. Okay, so this is the population, this is the empirical. Clearly, this is not the same as that. We want to know how close they are. So to motivate this discussion, I want to show you a diagram. This is what you would normally do when you conduct a survey. On the x-axis of this plot, we have the number of samples. 5 sample, 8 sample, 20 samples. And then on the y-axis, these will be the location of all these samples. Okay, so that will be the location of these samples. Now, if you only have 5 samples, okay, you only have 5 samples, then you calculate their average. The average can be high, can be low. Okay, so now. So let me do it this way. So here is your 5 samples, okay? And then these 5 samples, you calculate their average. So by calculating the average, I really mean that you take the sum of all these 5 data points, and then you divide by the total number. And imagine that you're only looking at the y-axis, okay? So that will give you 1 cross. So 1 cross will represent 1 empirical average coming out from 5 data points. Okay, so then tomorrow morning you wake up and then you collect another set of data points. it will still be 5 data points, but then they will not be located as this. Okay, so now you get another average. The average might be here, and then you get an average here, you get an average here. These crosses, they are the empirical averages found by calculating the average of 4 different configurations. Each configuration is that you close your eye, you go to the back, and then you draw 5 samples, and you ask what is the average of these 5 samples. And of course, they vary a lot because you only have 5 samples. Now, if you go on to this situation when you have 8 samples, then you have 8 dots, and then you know that because I have more samples, then the average should be closer to the true average. And so from these 8 data points, I'm going to calculate an empirical average. That will give me a green cross. That will be here. Okay, now I wake up and then I collect another 8 data points and I calculate the average again. I will get this cross. And you collect all these crosses, they will distribute like this. Why? Because here you have 8 data points to start with, and of course the deviation will be smaller compared to the beginning where you have only 5 data points. And you can also imagine that as the number of data points go from 5 to 8 to 20, when you have a lot of these data points, where's the average? Well, the average should be somewhere here. Okay? Compared to when you have only 5 data points, the average could be here. If I change another set of 5 data points, the average could be somewhere else. Here, the average will be very, very concentrated around the actual population mean. Okay? Now, you plot all these crosses, and you see that these crosses, they are somewhat random. That's actually what's happening when you calculate the empirical average. If you look at this formula, here you have a sequence of n random variables. You sum them up. This sum itself, it is a random variable because sum of random variables is still a random variable. I just don't know the distribution, but it is a random variable. And therefore, the random variable will have its own mean, it has its own variance, it has its own distribution. So here it shows you the diagram. When you only have 5 data points, that would be the realization of that random variable. Here you have a different realization of the random variables. You have different realization of the random variables. And so as the number of samples increases, you should expect to see a converging distribution. Okay, so all these numbers, they should converge to somewhere. And as n goes to infinity, we know that it's going to converge to the population mean. Okay? So now let's map this idea back to the learning case, right? So we have been saying that, look, you only have a training set, and then you calculate the training error. And if you only have a finite set of training samples, then the error that you calculate is not going to be a deterministic number, right? Because who knows if this particular training data set is going to give you this training error. But if you tomorrow morning you wake up, you collect another training data set, it's going to give you another training error. So which one is correct? Well, both are correct because they are just the realizations of the same random variable. Okay? So if you think in this way, then when you write your own paper, you should be paying attention to, because the training error that you're reporting is a realization of a particular configuration or the realization of a particular training set that you draw from the entire population set. Okay, so that number that you're reporting is just based on that. Okay, so we want to analyze this behavior as n goes to infinity. How quick will this variation? Okay, when you're measuring the standard deviation, how fast will these converge to 0? Because we want to know, is it 5,000 samples enough, or is it 10 million samples the right number to use? What is the minimum number of samples that I really need in order to get a certain guarantee? And here by guarantee, I really mean that you put an epsilon here. You say that, all right, I want my deviation, I want my standard deviation to be within an epsilon bar that I feel comfortable with. And I say, okay, what would be the minimum number of n in order to achieve this epsilon? So that's a legitimate question to ask. You can pose it onto machine learning questions and ask, I have this data set, what is the number of training samples we need? Okay, so this is just a numerical experiment that I'm drawing samples from a Bernoulli random variable, and then I'm just drawing yes and no. I draw a lot of these samples, and then here I have 100 sample, 1,000 sample, 10,000 samples, and so on. And these circles, they are the empirical averages. Okay, I calculate on the computer. As the number of training samples increases, then you can see that the empirical average, they actually converge. But one thing that you want to pay attention to is the red line here, it represents one standard deviation from the true mean. At any point, for example here, the standard deviation says that I am that close to my true mean. However, when you look at the actual sample, you do have a sample that's outside that standard deviation. That happens all the time because what you're guaranteeing is that you're guaranteeing only on this standard deviation. You can never say that it is absolutely certain that there is no blue circles that are outside my red line. You can only say with so much probability that the blue circles will appear outside my bound. Okay, so you can see that the convergence that we are going to talk about would be more probabilistic, not that they're deterministic, because all these circles, they are random numbers. Okay, so we can only say with whatever probability that this circle would be within this bound. So let's look at the math a little bit more carefully. Here is the empirical average again, and I have mentioned that this new random variable, it is random by nature, and therefore it has its own probability density function, and it has its own cumulative distribution function. So itself is a random variable, so you can talk about its own statistical properties. We can easily evaluate the mean of this random variable nu, and you can show that if you take the expectation of nu, that will give you this expectation over the summation over all the random variables xn, and then this 1 over n will come out, and you are taking the summation of all these individual expectations. And these individual expectations, because we assume that they're ID, so you have a mu here, and so you're just summing a bunch of mu's and then divide by 1 over n, that will give you mu. Okay, so therefore, here you can show that expectation of mu, this random variable, is just mu. Right? Now, if you try to go back one slide to here, you see that all these blue circles, they're moving around. They have their own distribution at whatever n. Okay, so for a particular n, you have a distribution. But then the mean of this distribution, it remains the same. Okay, so if you say, okay, I want to put an I here, I just want to look at 1,000 samples. Then you're drawing a cross section here, and then all these blue circles, they will form a random variable. Okay, it's a random variable that is constructed from 1,000 samples, and so this range will be the distribution of all the blue circles. And then you look at the mean will still be the same mean because you're assuming they're ID. Okay, it's just that the standard deviation is changing as your n grows. Okay, so the question that we want to ask here is, what is the probability that your nu is going to deviate from mu? If we can analyze that, then we are in pretty good shape, because then we can quantify for how many samples I will guarantee you to have certain tolerance. So what is the probability that we want to analyze? Well, whenever you talk about probability, it has to be the probability of a certain event. And here I'm defining a bad event. Now, what do I mean by bad event? Let's look at this equation. You have nu, that is your random variable. And then you have mu, that is your population mean. And you want to calculate the deviation from nu to mu. And you put the epsilon value, absolute value here, and then you measure whether this is bigger than certain epsilon. Okay? Now, when will this be bigger than epsilon? Well, it will be bigger than epsilon when you are in this situation. So this is the population mean, and this is the standard deviation. And then the mu is here, and then the nu is this is a random variable, so this is nu. Okay? So if you say that I want to put a epsilon to be somewhere here, this is my epsilon. okay, then I'm asking whether this black dot will be outside this epsilon, will be above the epsilon or below the lower epsilon. Okay, so if that happens, it really means that my nu is appearing outside the range of epsilon, and I call that a bad event because then you're outside the range that you cared about. Okay, so this is called a bad event. Okay, I define it using a B. B stands for bad. Okay, bad event. Now, since it is a bad event, do you want this probability to be big or do you want it to be small? Of course, you want it to be small, right? You want this probability of bad event to be small. Then we ask, how small do you want, can it be? Okay, so we want to upper bound by this probability of bad event by a certain number, I call it delta. So you want to find a delta such that this bad event probability is upper bounded by delta. And as this delta reduces, you will be more and more conservative, right? And also, hopefully, that this delta will change as a function of n. That means as the number of samples grows, this delta, I want it to drop, okay? Because otherwise, how can you bound this bad probability? Okay, so now this probability can also be interpreted the other way around. You can say that what if I don't want to use the bigger than sign, I want to look at the probability that all my samples, they are inside my tolerance level. Then it becomes a good event. And what is the probability of getting good event? Of course, the probability of getting good event has to be at least 1 minus delta. So if you ever read a machine learning paper, what you will normally see is that this result, this theorem is guaranteed to be true with probability 1 minus delta. Okay, so these are all the probabilistic statements saying that the thing that I'm going to prove you is going to be true with probability 1 minus delta. And normally this delta is very, very small. It is a function of n, and as n grows, this delta becomes extremely small, and so you have an extremely high probability of getting a good event. Okay, so these kind of statements, they are useful when you study machine learning problems. Why? Because there's nothing deterministic in the statistical world. Everything that you want to quantify will be subject to the probability, subject to the randomness that you have in your data set. So this statement, you need to get used to it because in our course, and even if you go out our course, you will see these kind of statements very often. So I'm going to introduce you two sets of very simple probability inequalities. The first set contains two inequalities. One is called the Markov inequality. The other one is called the Chebyshev inequality. They can be proved in one page each. Okay, it's very simple proof. Let's talk about the Markov inequality first. This is an undergraduate result. So it says that if you have a random variable x bigger than 0 and then you have epsilon bigger than 0, then the probability of x bigger than equal to epsilon is upper bounded by this expectation of x divided by epsilon. Okay? Now, this is an extremely general result that applies to pretty much all the random variables that are non-negative. So how do you prove that? Well, you can move this thing over the left-hand side, and you start from here. Then you realize that this is just epsilon times the probability of x bigger than equal to epsilon. And then here is just the integration of your density function from epsilon to infinity. Then you can move, of course, you can move the epsilon inside the integration. Then you have integration of epsilon times your density function. And then this epsilon is, of course, less than any x that you're integrating because you're integrating your x from epsilon to plus infinity. And of course, this epsilon has to be less than x, right? Because the x that you're integrating is over here. And so you have this less than equals to with this x here. Then what? Well, then you can also change the epsilon to 0. Because this is a bigger range of numbers since your x is positive. And so you can replace that, and then you just end up with this integration of x times px. That's what? That is just expectation of x. Okay? That's the definition of the expectation. So here is the Markov inequality. It's very easy to prove. It's only taking me 1 to 4 lines. Okay? Now, this Markov inequality will be very useful when we go to the next one. It's called the Chebyshev inequality. The Chebyshev inequality says this. If you have a sequence of variety random variables, and then each one you have the same mean of mu, and then they have the variance of sigma square, then we ask, well, okay, what is the deviation between the sample mean compared to the true mean bigger than epsilon? And we can show that it's actually less than or equals to the sigma squared divided by n times the epsilon square. Now, without going through the proof, let me just tell you how important is this result. Okay? So this result can be derived from the Markov inequality. The proof is down here. But if you look at this equation, this one says what? This one says that the population mean mu is here. I want to measure the deviation between my sample mean and the population mean. The tolerance level is epsilon. This is exactly a bad event that we have been talking about. On the right-hand side of this inequality, there is a ratio. This ratio says that in the numerator, I have sigma squared. Sigma squared comes from my original random variable x. X has a variance of sigma squared. Now, in the denominator, I have my tolerance level epsilon, and I also have a factor of n. Okay? Now, just assume that the sigma squared and epsilon squared, they're fixed. They're just some numbers. They're fixed. They're not going to change. And then you are going to make this n bigger and bigger. Why? Because you're considering the situation where you have more and more samples. So as n grows, what will happen to this upper bound? It will go to 0. It will go to 0 linearly, right? So as n goes to infinity, this quantity will go to 0. In other words, what is the probability of having this bad event? Now remember, this bad event is upper bound by some quantity, and that some quantity is going to 0. And of course, this bad event probability will go to 0 as well. Okay? So it gives you a very, very simple tool to say that as the number of training samples going to infinity, my sample mean is going to converge to my population mean with this rate. Not a very, very good rate, but it's converging. At least I can claim that it's converging. It's going to 0. All right, so this is giving you some hints of why in many, many situations, when we look at the machine learning algorithms, we want to have the training set to be as big as possible. It's because that when you have a lot of training samples, then the training loss, okay, think about in this case, your nu will be your training loss, okay? Your mu will be your testing loss. So if you can guarantee that your training loss and the testing loss is going to 0, then you are in good shape, because then you can guarantee that whatever your training can be generalized to whatever you're going to test. Okay, so this is a very, very important result. It's a very weak inequality, but it at least brings out the spirit of what we want in this machine learning regime. Now, that also shows you the importance of having this in this probability model. Okay, so if remember in the machine learning model, we have this probability distribution, and I have been emphasizing that this probability distribution that is used to generate both the training set and also the testing set. And there should be a correlation between the two. If there is no correlation, then you run into a deterministic situation. And if that happens, then learning is not feasible. I just gave you a kind of example last time. Okay? And therefore, if you want this to work, then you must have a probability distribution. Once you have that probability distribution, you run into an analysis like this. You want to quantify the probability of getting a bad event, and hopefully it will be upper bound by some quantity, and that quantity will go to 0. Okay, so how do we prove the Chebyshev inequality? The proof is actually probably just one line. Okay, so what you do is that you look at this inequality. This is the bad event of absolute value between nu and mu. You can always put a square on the two sides of this event. That will not change the event, because the square is, so if you put a square here, then it's the same event. Okay. Now, if it is, when you put a square over here, then what can you do? Well, if you have the probability of nu minus mu, a square bigger than epsilon square, what do you have? Well, just apply the Markov inequality. The Markov inequality says then I can have the expectation of nu minus mu square divided by epsilon square. Okay, so that is the Markov inequality, and then the numerator will become sigma square because that is just the random variable itself, and then the denominator you have n epsilon square. The n will come from the sample average. Okay, because the variance of nu is the expectation of nu minus mu square. And so this nu is 1 over n summation of xn minus mu. So you have a square term here, right? And then the 1 over n has to come out as this. Then you have the variance of xn. Okay, so therefore you have sigma squared divided by n that comes out from this equation. Okay, so this is the Chebyshev inequality. It's very, very easy to prove. Okay, the message is actually pretty strong because I have just showed you that even in the machine learning situation, this inequality will tell you some useful message. One point that you may want to ask is that why do I want to square the term? Why can't I just apply Markov inequality to this absolute value? Because Markov is applicable whenever your random variable is positive. I'm taking the square because I want to evaluate the expectation of a square. If I only have absolute value here, then I don't know how to evaluate the expectation of the absolute value of mu minus mu, okay? If you have a square, then it becomes the standard deviation, or it becomes the variance. It's a lot easier to calculate. So this is the Chebyshev inequality, and we can ask how good is the Chebyshev inequality. As I said, that the Chebyshev inequality is actually very, very weak inequality. It doesn't really capture the reality. So here is a cartoon diagram showing you what's happened when the number of training samples grows to infinity. So this is the number of training samples, and then here is the probability. The Chebyshev is the upper bound that is given by this red line, and then the green crosses, they are the actual empirical average. Okay, so the empirical average, you measure the probability, you do this experiment, all the green crosses, they are living here. And so you can see that yes, the Chebyshev inequality is actually a correct, a valid upper bound, but then this upper bound is just too loose. Okay, it can tell me something, but it appears that it to be too loose, that it may not be reflecting the reality. That's why people have been working really, really hard to find better and better inequalities that can really explain this behavior. That will go to our second part of the course, this lecture on advanced inequalities. But before we move there, let me comment on two things. One is called the weak law of large number, something that you might have learned in your undergraduate course. The weak law of large number is exactly quantified by the Chebyshev inequality. It says that if you have a sequence of ID random variables with a common mean mu, and then you let this m of n as the sample average, then for any epsilon bigger than 0, if you take the limit of n going to infinity of this probability, it will go to 0. Okay, this is a fairly easy result because you look at the Chebyshev inequality, you put the limit on the left-hand side, you put the limit on the right-hand side. As n goes to the infinity, then the limit on the right-hand side will go to 0, and that's why you can have a 0 here. So the proof is one line. Now, this is called the weak law of large number. The reason is that this limit is actually outside the probability. Okay, this is called weak because as n going to infinity, you're not guaranteed that all the samples are within the bound. Okay, you're still saying that the probability that one samples will go out is just very small, but you cannot eliminate the possibility. So that's called the weak law. Now, the alternative is called the strong law. The strong law says that, in my language, okay, you're just flipping the limit, and the probability. So instead of putting the limit outside, you put the limit inside. Now, the strong law says that the probability having this bad event is 0. It's absolutely not possible to have a bad event, when n go into infinity. Okay? Now you ask, why is this called a strong law? Well, look at this. The strong law is a lot more stronger than the weak law because you're looking at this limiting object. Okay. Now, originally you're looking at the limit is outside, is measuring the probability of this bad event. However, now you're measuring a what? You're measuring probability of some event, okay, some super bad event or super good event, okay. So this event itself is a limiting object. Okay, so first of all, you need to look at the sequence of events, and then you're looking at the limiting object of the sequence of events, and then you're measuring the probability outside. Previously, what you're doing is that you are evaluating the probability of a bad event, and then you have a sequence of numbers, and then you take the limit. That is a lot easier. Any real analysis results can be applied to here. This is a lot harder. The reason is that this is a sequence of events, and then you need to analyze the limit of the events, and then you take the probability on the limit of that event. So that is a lot harder, okay? For certain type of random variables, strong law will hold, but for other cases, weak law is a lot easier to satisfy. For this course, we do not need to differentiate these two, okay? We will stick to the weak law, and then we will derive all the results based on the weak law.